Hi everyone, welcome to the talk. I'm glad to share our UBITect work here, which is a precise and scalable method to detect use-before-initialization bugs in Linux kernel. I'm the first author Yizhuo from UC Riverside, and I'm working with Srikanth and Zhiyun. This is a joint work from UC Riverside and US Army Research Lab. First, what is use-before-initialization bugs? Here is an example. In this piece of code, a local variable backlog is defined in line 4 without any initial value, and if the condition in line 5 stands, it's initialized. Otherwise, it remains uninitialized. Uninitialized does not mean there's nothing inside, but means it stores whatever value left in the stack. However, the variable backlog will be used in line 9 in the if condition. Moreover, in line 11, it's dereferenced. If the previous data on the stack has a malicious address, then the program will jump to and execute the malicious code. We summarize this scenario as figure 2. Each circle is a program point, and the arrow stands for the possible execution path. If there is a variable that reaches the use without any initialization, then we call it a use-before-initialization scenario. From this graph, we need to address that UB bugs happen along with specific paths, and we need to make path-sensitive analysis for precise detection. UB bug not only stands for some program error, but introduces the security impact as well. According to different use of uninitialized variable, UB causes different security risks in Linux kernel. First, if a variable is an uninitialized pointer and it makes the program jump into prepared malicious code, then it could cause arbitrary code execution. Second, if it jumps to a random address, then it causes a system crash and denial of service. Third, if in copy to user, the content of the source pointer is not fully initialized, then it causes information leakage. If the uninitialized variable is used as an array index, then there is out-of-bound memory access. After those security risks are discovered, there appears too many solutions. Those solutions can be divided into two categories: mitigation and detection. The common mitigation is to zero in the located object, such as unison and safe-init. However, the initial value 0 could cause non-pointer dereference. Moreover, the initial value 0 sometimes represents unique meaning. So, zeroing the object cannot fully mitigate UB bugs. But instead, detecting the UB bugs and let developers decide the initial value is a better solution. Regarding bug detection, there are indeed some other work. First, applying the intra-procedure static analysis to detect UB scenarios. Example includes some compiler options and CPP check. In this design, it ignores the UB bugs that happens across functions. The second method is the symbolic execution. It is a path-sensitive analysis, but suffers from the path explosion. A typical example is clone static analyzer. The third method is a dynamic analysis, which just covers a certain amount of the path and misses some bugs. From the previous work, we can find that the main challenge to detect UB bugs in Linux kernel remains in the conflict between scalability and precise analysis. Let me explain them one by one. First, detecting the UB bugs in Linux kernel requires a scalable analysis because it has a large code base and complicated call relations between functions. Also, there are many possible paths from the variable declaration to its use. If we consider the UB scenarios that happens across functions, the path-sensitive analysis is not possible now. Previous flow-sensitive but non-path-sensitive analysis scale to the Linux kernel, but they have many false positives. To solve this challenge, we propose an UBITect approach, which is a UB bug detector. It combines the qualifier inference and symbolic execution to automatically find bugs in Link's kernel. In this page, I will show you some high-level ideas, and the details of these two methods will be explained in the later pages. So first, let's see how those two components address this challenge. Qualifier analysis adopted bottom-up, summary-based analysis, which means each function is analyzed only once. This enables us to do inter-procedure analysis in the whole kernel. Then, the qualifier analysis is precise, as it uses inter-procedure, flow-sensitive, field-sensitive, and context-sensitive analysis. Third, qualifier analysis generates some guidance to help symbolic execution to reduce the path searching space, which helps to improve the scalability. And under-constrained symbolic execution is path-sensitive, which promises the precise analysis. Combines flow-sensitive qualifier analysis and path-sensitive symbolic execution to automatically report UB bugs in Link's kernel can be relatively scalable and precise. Then let me detail some content shown in the last page. First, what is qualifier? Qualifier, or type qualifier, is a kind of type annotation. It has two functions. First, it describes some additional information of the annotated variable type. Second, it ensures the correct use of the tag type. A well-known example in C language is const. Const is a type qualifier. If we define a variable annotated with a const type, then it means the variable is a constant. This is additional information. Well, this constant cannot be changed. This ensures the correct use of the const type. Back to our work, we introduce two qualifiers, init and uninit, to annotate the type. And we make rules that once the uninit variable is used, we raise a warning. Let's look at the example. When a variable is declared, it's annotated by uninit, and as the execution of the program, in a place it's assigned a value, its state is changed into init. But when the program branches merge, if there is an incoming edge showing it's uninit, we update its status as uninit. And in each place of the use, if we see an uninit variable, we raise a warning. The second thing we did along with the qualifier analysis is generating symbolic execution some guidance. Symbolic execution, or SE, is a kind of program analysis method. From the program entry, it calculates under what input it can go to a specific execution path. In our method, we want to find such a path from declaration to the use. Along this path, there is no initialization to a specific variable. Therefore, in our guidance, we will tell SE the variable declaration, the use, and the place that it gets initialized. If SE encounters those places, then it can stop the exploration. Using this method, we narrow down the SE searching range and speed up the exploration process. For complete qualifier inference rules, please refer to our paper. We use slightly different description here just for easier understanding. Next key approach we use is bottom-up style, summary-based analysis. First, we compute the global call graph, and start from the leaf function, we do analysis and summary. Later, when we analyze the caller, instead of analyzing the callee function again, we refer to the summary and understand what will happen to the arguments when we do a function call. This is a bottom-up part. Let's use F3 as an example to describe how the function summary works. In F3, we have two arguments, an integer a and a pointer pa. In this function, the object of pa is initialized, and variable a is used in the if condition. Therefore, to be UB bug-free, the caller of the F3 should meet the requirement that pa passed in is initialized. The same as a, because it is used in the if condition. Also, because the object of pa is updated into 4, the object PA points to is set as initialized. Using the same method, we also summarize the return value as initialized. Now we got the function summary. In function summary, we care about two kinds of information: requirements and update. Requirements record the information that if a caller wants to be UB-free, what preconditions that the arguments should meet. An update tells the caller that after the function call, what will be changed to the related variables. When we analyze the upper caller, we will do two things. First, we check if the caller passes us the arguments that fulfill our requirements. If not, we raise a warning. Then we do the update. The caller will refer to the update information and update the qualifier of the corresponding variable. Putting them together, we have the whole workflow. We combine the kernel source code into LVM IR, construct the call graph, and do the bottom-up style qualifier analysis, generating warnings and guidance, and finally use symbolic execution to find the feasible path. If the path exists, then we report it as a bug. Besides the bug itself, we also report the corresponding path to the developer. In each qualifier analysis, we did the normal pre-processing such as point-to analysis. Our implementation is based on LVM 7.0.0 and has more than 13K lines of code. The symbolic execution engine is clean. We did 3 evaluations about UBITect. First is to test if UBITect can detect all the known UB bugs before. Second is its ability to detect new UB bugs. Finally, we did comparison with previous open source bug detection tool, CppCheck and Clown Static Analyzer. In the first evaluation, we collect the bugs from 2013 to Linux version 4.14, which includes inter-procedure and intra-procedure analysis, and UBITect can test them all. In the second evaluation, we test the Linux version 4.14 with all ESEC and it covers more than 13K files and more than 600K functions. Qualifier analysis costs 1 week to finish all the analysis. To prioritize the warnings, we set the time limit and memory limit to symbolic execution, because we think if symbolic execution could find the bug quickly, then it will be easier for human to inspect the bug. We manually inspect the bugs that UBITect reports and identified 138 bugs, in which 118 are not patched. We submit the patches or email the Linux maintainers and got 52 confirmed. For more details, please refer to our paper. UBITect is not perfect. It suffers from false positives. The reasons include some incomplete guidance, imprecise indirect call resolution, some corner cases due to LVM optimization, and finally some limitations of the symbolic execution. In evaluation 3, we did a comparison to other 2 static analysis tools. First is the CppCheck. It does intra-procedure analysis. And the second is a Clown Static Analyzer, which does inter-procedure but not inter-files analysis. We select the files which UBITect reports bugs and let them analyze those files. CppCheck reports 164 bugs, but only 2 true positives. CSA reports 17 bugs, which has fewer false positives, but low number of bugs. This again shows that one method is not sufficient to detect UB bugs. Here is a bug that UBITect found in driver's media USB. In line 3, it declares a structure type QControl and only initializes the ID. Then the rest of the structure is supposed to be initialized while function call. However, the rest of the structure could be uninitialized if the function fails. Then in line 7, the flags field is used in the if condition. Therefore, UBITect reports a warning here. In this example, we want to show that the field-sensitive analysis and inter-procedure analysis across the files is necessary. Now let's conclude the work. First, UBITect causes critical security issues, and zeroing the variable cannot fully mitigate them in its kernel. Second, we propose a UBITect approach, which is a precise and scalable tool to detect UB bugs in Linux kernel. Finally, we got 52 new bugs confirmed in Linux. And I'm happy to take questions in discussion session. Thank you.